Special cases. In solving linear programming problems, one of the following cases will occur. Number 1, the LP has a unique solution. Number 2, the LP has an infinite number of solutions. This is the case of alternative optimal solutions. Number 3, the LP is infeasible or no feasible solution. And number 4, the LP is unbounded. We will explore cases 2, 3, and 4. Alternative optima. This happens if the LP has an infinite number of solutions. Graphically speaking, we can see this case when the objective function line, or the isoprofit line, is parallel to any of the constraints. Given that the constraint is not redundant, for example, considering the following LP, max sub z is equal to 3x sub 1 plus 2x sub 2, such that 1 over 40 x sub 1 plus 1 over 60 x sub 2 is less than or equal to 1, while 1 over 50 x sub 1 plus 1 over 50 x sub 2 is less than or equal to 1 as well. X sub 1 and x sub 2 are both greater than or equal to 0. From this example, we can see that the objective function has a slope of negative 3/2. Given the slope-intercept form of a line, y equals mx plus b, where x sub 1 is x sub 2 is y, and z is the b. By examining our constraints, we can see that the first one also has a slope equal to negative 3/2. It is also important to note that the constraint parallel to the objective function must be a binding constraint before concluding that the LP has infinite solutions. In our example, since we have a maximization problem, any point along the first constraint can satisfy the LP. Example given, 40, 0. But if it was a minimization problem, we can see that the point 0, 0 is a unique solution, even though the first constraint is parallel to the objective function. Graphically, we can see that there is indeed an infinite number of solutions, since the isoprofit line will coincide with the first constraint before leaving the feasible region. When using the simple X algorithm, it is still easy to see if alternative optima are present. At the optimal tableau, we can say that the LP has alternate optima if there is a non-basic variable that has a 0 value of 0. Note that in normal cases, the z value of non-basic variables are non-zero. This means that we can make it enter the basis without affecting our optimal value, since there would be no row operation for the z row. We can let S2 enter and make X2 leave the basis. And the process of finding alternative optimal value continues. Infeasibility. Infeasibility occurs if the feasible region contains no points. For example, from our previous LP, we add two more constraints. Max z is equal to 3x sub 1 plus 2x sub 2, such that 1 over 40x sub 1 plus 1 over 60x sub 2 is less than or equal to 1, while 1 over 50x sub 1 plus 1 over 50x sub 2 is less than or equal to 1. X sub 1 is greater than or equal to 30, and x sub 2 is greater than or equal to 20. X sub 1 and x sub 2 are both greater than 0. The graph of the LP is shown in figure 2. As you can see, there is no feasible region. We cannot find any value that satisfies all of the constraints simultaneously. Since this LP has an empty feasible region, this means that the LP is infeasible. In the simple X algorithm, you will see the infeasibility when you use the two-phase method, or the big M method, and the artificial variables that you introduced in the LPs are not equal to 0. This topic is explored further in two-phase and big M virus videos. Unboundedness. For a max problem, unboundedness occurs if it is possible to find points in the infeasible region with arbitrarily large z values. Graphically, we can see this by moving the isoprofit line in the direction of increasing z, but never leaving the feasible region. For example, consider the following LP. Max z is equal to 2x sub 1 minus x sub 2, such that x sub 1 minus x sub 2 are less than or equal to 1, while 2x sub 1 plus x sub 2 are greater than or equal to 6. X sub 1 and x sub 2 are greater than or equal to 0. By looking into the LP, we can increase the value of x sub 2 to infinity. But this alone will not make sense since we will have a negative z value. But if we will increase both x sub 1 and x sub 2 infinitely, but still maintaining a difference of at most 1, we can realize a z value of infinity. We can see it clearly through the graph of the LP. We can see that we can move the isoprofit line indefinitely, increasing the z value without leaving the feasible region. Therefore, we have an unbounded LP. We can also see unboundedness when using the simple x algorithm. If there exists a non-basic variable at any iteration that can enter the basis, but no variable can leave the basis, we can say that we have an unbounded LP. For example, take note, this is a BFS based from the graph of the LP. Make x1 enter and s1 leave the basis. We can see from this iteration that we can let s2 enter the basis, but if we do this, we will not be able to find the leaving variable. This case implies that we have an unbounded LP. Additional, we can say that an LP is unbounded if the feasible region where the isoprofit line moves is also unbounded. But an unbounded feasible region does not necessarily imply that we have an unbounded LP. Take the following as an example. Max z is equal to 2x sub 1 plus x sub 2, such that x sub 1 minus x sub 2 is less than or equal to 1. 2x sub 1 minus x sub 2 is less than or equal to 6, and x sub 1 and x sub 2 are greater than or equal to 0. We can see that we can just increase the value of x2 infinitely to get a higher z value. This is an unbounded LP. But what if we make this a minimization problem? We can see that we cannot make the value of x2 infinitely high, since that would just be counterproductive. We can solve this graphically or by intuition, and we get that the optimal solution for this is the point 0, 0 with a z value of 0. The LP still has an unbounded feasible region, but we found an optimal solution. Degeneracy. Another special case in linear programming is degeneracy. An LP is said to be degenerate if one of the basic variables in a basic feasible solution takes on a 0 value. This is caused by redundant constraints. Graphically, we can see a degenerate LP if there exists a feasible corner point where there are at least 3 intersecting constraints. At least one must be redundant. Consider the following LP. Max z is equal to 5x sub 1 plus 2x sub 2, such that x sub 1 minus x sub 2 is less than or equal to 0, x sub 1 plus x sub 2 is less than or equal to 6, and x1 and x sub 2 are both greater than or equal to 0. We can see from the LP and the graph the constraints x sub 1 minus x sub 2 is less than 0, x sub 1 is greater than or equal to 0, and x sub 2 is greater than or equal to 0, are all binding at point C. Since at this point x sub 2 is greater than or equal to 0, is binding and redundant, there will be more than one set of basic variables. When we use a simple x algorithm to solve this LP, we can clearly see how the degeneracy works. In the first iteration, we can see that the value of S2, a basic variable, is 0. You can imagine this iteration as point C in the graph. From this, we can say that the LP is degenerate. We now let x1 enter and S2 leave the basis. We can see that the z value is not affected. We just had another set of basic variables, still pertaining to the point C in the graph. We now let x2 enter and S1 leave the basis. We now arrived at our optimal solution. Additional information. Since we were able to escape the loop or degeneracy, we call this temporary degeneracy. Otherwise, if the loop continues forever in the final tableau, it is called permanent degeneracy. The extra iterations that degenerate LP need need to arrive at the optimal solution makes the simple X algorithm often an inefficient way of solving degenerate LPs.